Let's move forward and discuss some more topics, and today we will discuss catalysis. And before that, we talked of adsorption, right? There are some uses of adsorption. First, it is used in dehumidifiers. Second, in face masks. Face masks, I shall discuss this. You might have heard today that China is claiming that they have found a nanomaterial which may absorb this coronavirus and decrease its efficiency to 90 to 95% or 99%. These face masks, actually there are some particles, these nanomaterials, which are a mask like this. It's a layer of this nanomaterial tries to absorb the virus and deactivate it. Third use of this adsorption process, where it is used, it's used to create high vacuum. For example, if we try to create vacuum in this chamber, this chamber over here, we want to create a vacuum, we will use a vacuum pump and send all the air out, but there may be some traces of air which will be present over here, so we'll put some activated charcoal, which will try to absorb this traces of air, and we will have a perfect vacuum. Not perfect vacuum, it's not possible, approximately perfect vacuum over here. Now let's move to our topic, catalysis. See, let's take a container, and there is one type of reactant A and another type of reactant B. They are well mixed here in this container, and they react here and produce some product C. Now this we can represent this reaction like this: A plus B gives C. Now let us assume that this reaction takes 10 minutes. Now we can use a foreign material, for example, and put it in this container in which the reaction A plus B giving C is taking place. By adding this foreign material, this time of reaction, for example, it was taking 10 minutes to form 1 mole of C, for example. Now it will take only 7 minutes. What happened? This foreign material, let's represent this by D. This D increases the rate of reaction between A and B. This D is known as catalyst, and this process is known as catalysis. I hope it's clear. Let me discuss. See, now actually there are some characteristics of these catalytic particles. Characteristics. First, it does not initiate reaction. That means catalyst initiate reaction. That means by adding catalyst to some reaction A plus B, we cannot start this reaction by adding this D. This D will not start this reaction. It will just enhance its rate of reaction. It will not start, it will not initiate this reaction. This is the first characteristic of this catalyst. Second characteristic, second one. See, let's take a reversible reaction now. A plus B gives C, and C in turn gives A plus B. See, for example, there is A plus B which gives some C, and this C decomposes also back to A plus B. Now when the reactants, only the reactants are present, A plus B, their concentration is, A's concentration is maximum, B's concentration is maximum, and initial concentration, that means C naught, it is 0. Now A plus B will try to form some C, that means the concentration of this C will increase, and after some time this C will also try to decompose. This is the basic of reversible reaction. I hope you know this. This C will try to decompose in A plus B back, and after some time the rate of this forward reaction, that means formation of C, will be just equal to the decomposition of C back. That means there will be a state of dynamic equilibrium there. Dynamic equilibrium. See, now adding catalyst in this reaction, what will be the role of this catalyst? This catalyst, when we add it to this reaction, this will just, see, let me make it in a next slide. See, when we add catalyst A plus B, we add some catalyst D to this reaction. Remember, this A plus B gives C is a reversible reaction. See, this D will just take this system fast to the state of equilibrium. It will not disturb the equilibrium. It will just take this system as fast as possible to the equilibrium state. That means A plus B, initially they were giving 10 moles of C. For example, in 10 minutes they give 2 moles of C. Now after adding this catalyst D to this system, they will give 2 moles only, but in 7 minutes or 6 minutes, for example. That means by adding this catalyst to this reaction system, the state of equilibrium, the rate at which this system attains equilibrium, is just enhanced. This is the role of catalyst. Third, at the end of the reaction, this catalyst at the end of the reaction is recovered back. That means it will be same as it has been added into the system. It will not change. That means if we add 10 moles of catalyst, we will get 10 moles of catalyst back. That means this catalyst does not take part in the reaction. It will not take part in the reaction. It will just enhance the rate of reaction only. I hope it's clear. Its physical properties may change. Maybe its state will change. Its shape will change. But overall, the properties of catalyst will remain same. I hope it's clear. Next point. The catalyst is very specific in nature. That means one catalyst, if we use a particular type of catalyst, for example, nickel is a catalyst. Nickel is used as a catalyst. This nickel is not in the position to catalyze each and every reaction in this universe. This nickel will catalyze some particular type of reaction only. That means the catalyst is specific in nature. It will catalyze only some particular set of reactions. It cannot catalyze each and every reaction. A particular catalyst cannot catalyze each and every reaction. It's clear.